Okay, so you're all over the place. Okay. All of my favorite places. Yeah. My husband's birthday present, or no, it's his Christmas present, was once we can travel again, is a trip to London.
Yeah, if it's still here.
Yeah. No, I lived in Hampstead when I was a child.
Yeah, nice.
So, yeah. Yeah, first for 1 year, and then went back many times to live there for summer. My father was a professor, and he was studying the British educational system. He's an economist who.
Live streaming onto YouTube now, so don't reveal too much about your family that you don't want the whole world to know.
Okay.
We've got less than a minute, I think, Sally, so I'll kick off at 3 o'clock exactly.
Okay, perfect.
Yeah. It's a real conversation stopper, isn't it?
Yeah.
Okay. Welcome everybody to this Earth to Earth seminar. Thanks for joining us today. It's the 14th of January. I have a great talk for you in a minute. This is part of a series. If you're interested in other talks and seminars on the series, you can visit the website, earth2earthseminar.com. As a reminder, any UK institution that wants to participate in organizing the series can contact us by email. And the mission of Earth to Earth, which is gaining lots of interest, is to engage the UK geosciences community with inspiring science from internationally leading researchers. We do this while promoting inclusivity and diversity, and we try to support also the advancement of early career researchers and highlighting geoscientists' contributions to addressing global environmental challenges. And Earth to Earth seminars take place regularly, I think roughly every 2 weeks. They're open to anyone. You can join via Zoom webinar, or you can join via the live stream to YouTube. And on to today. A reminder that the lecture today will be recorded and will be available on the YouTube channel. I think it is right now, with closed captioning. Calendar links and further information are on earth2earthseminar.com. During the seminars, can we ask you to follow our code of conduct, which you can find on the Earth to Earth webpage. If you're interested in asking questions, please use the question and answer Q&A channel at the bottom of your Zoom window. You can post these questions anytime, and you can vote up questions as you like. We have 10 minutes at the end, roughly, for me to relay questions to the speaker today. And now it is my pleasure to introduce today's speaker. We're very fortunate to have from California, Professor Sally Benson. Sally joined Stanford University in 2007. She's the co-director of Stanford's Precourt Institute. She's a professor in the Department of Energy Resources Engineering in the School of Earth, Energy and Environmental Sciences. She studies technologies and pathways to reducing greenhouse gas emissions, including geological storage of CO2 in deep underground formations and energy systems analysis for a low carbon future. So this is really on message. She also directs Stanford's Global Climate and Energy Project. So Sally is going to be talking today about geological controls on storage of CO2 in sedimentary basins. And it's a really important topic of for our decarbonisation and net zero ambitions. So I'll hand over to Sally, who's going to share her screen and start talking. Thanks, everyone.
Okay. Well, terrific. Thank you so much, Michael. And it's terrific to be with all of you here today. And I'm going to go ahead and share my screen. There we go. And there we go. Okay. All right. So it's about 7 o'clock in the morning for me. I might take a little while to really wake up, but anyway, I'm really pleased to be able to talk with you today about geological controls on storage of CO2 in sedimentary basins. And what I'm going to be doing is just giving you a particular set of examples of some work that we have done at a variety of scales, which illustrate just how important it really is to have a great understanding of the geology, and in particular the details of the geology. And I'll just sort of say one more thing. So I did my undergraduate studies in geology, and then I went on to study essentially reservoir engineering. And if you look at who are the professionals engaged in these topics, they actually have sort of migrated to being more chemical engineers and mechanical engineering experts who really focus on the details of the modeling and the mathematics and mass and energy balances and so forth. I think we really need many more geoscientists who really understand the structure of the earth to contribute. So hopefully this will be a pitch for all of you who are geologists to realize that you have an incredibly important role to play. And for one, I always love it when I get a student who has a background in geology, but is also interested in modeling, because it really brings together these two critical strengths that are needed. So that's kind of the plan. Before jumping in, I just want to say all the work that I'm going to be talking about today was done by an amazing team of postdocs and students. Two of them moved on to be right in your backyard, Sam Kreber, or Kreber, as I think he's often called, and at Imperial, and also Ronnie Pinney, really important contributors, especially in the early stages of the evolution of the kind of thinking that I'll be talking about, and then a great team of students, and also support from government and industry for all this work. So thanks to all of you. None of this would be possible without you. Okay, so I'm going to be talking about geological storage of carbon dioxide, but it's really important to provide context, of course, and the context is that as the consequence of emitting so much carbon dioxide into the atmosphere, we've now had over 1.1 degree C of warming. And that doesn't sound like such a big deal, but in reality, the consequences of even 1.1 degree warming are enormous in terms of changing weather patterns and flooding and wildfires. And really, I think it's fair to say that already climate change is sort of wreaking havoc on society today. And the only way that we can address this problem is to completely and dramatically and quickly reduce emissions of carbon dioxide into the atmosphere. And this is just a chart. This is from the IPCC uses these what are called integrated assessment models to look at different pathways and in the energy system and the global economy, and to ascertain how much warming there would be. And so looking at this chart here, the pathways that we need to be on are shown by the green and perhaps blue curves here, where essentially now we need to be very close to peak emissions. We need to get to net zero sometime in the latter half of the century. And then thereafter, we also are going to most likely need to remove carbon dioxide from the atmosphere. And one of the ways that can be done is to scrub carbon dioxide from the atmosphere and then pump it underground for storage. So in the short run, trying to decarbonize industrial sources and electricity using carbon capture and storage, and then eventually looking to negative emissions to accomplish that. So we've got a lot of work to do. There's always this big question of scale. How much carbon dioxide capture and storage do we need? And this is an analysis that was done by a big team, international team, looking at this question in 2018. And we looked at all of the emission sources, and we identified those which we believe there are pathways to substituting fossil fuels with another source of energy that would meet that need without emitting CO2, but that there are a significant number of emissions that are going to be very difficult to eliminate because we just don't have good substitutes. And so examples would be shown here. This is load following electricity. So it's certain that wind and solar and hydro and the renewable generation is going to be the significant and perhaps even major source of electricity. But there are real serious challenges about reliability. And it appears that, at least, for example, from detailed studies that I've done, that you need sort of 20% or between 10 and 20% of electricity needs to be available on demand. And carbon capture and storage, for example, on natural gas plants is a very good way to do that. There are also things like cement and iron and steel that we don't have good substitutes today. And then, of course, we have things like shipping and aviation and heavy-duty road transport that we don't have many good alternatives today. So if you add these up, it turns out this is about 9.4 billion tons per year of CO2 emissions, or about 25% of the emissions from burning fossil fuels for industry. So that sets the scale. So if you think about that 9.4 billion tons a year, it's quite large and really sets the scale of the challenge. So I think almost everybody is familiar with carbon capture and storage now, but just briefly as a reminder, and then for those of you who this may be new to you, that the idea is that there will be a variety of industrial emission sources, concentrated CO2 emissions at a large scale that could be captured using chemical scrubbing technology, or there are a variety of other technologies. That carbon dioxide is captured and then compressed into a liquid, which then when you can pump that deep underground. Basically, one simple way to think about it is put it back where it came from. All of these fossil fuels come from oil, gas, coal, deep underground. The carbon dioxide can be pumped back underground at appropriate sites where it then warms up and it becomes a supercritical fluid. So the idea is that you, again, put CO2 underground. Saline formations, these are basically, one could think of it as a salt water filled sandstone formation as an example, but it could also be put in oil reservoirs or gas reservoirs as well. So if we think about the requirements for storage, one can develop the very long list, or you can develop the short list. I don't know, my short list is that you want negligible leakage, you want no groundwater impacts, and you want no damaging seismic events. So those are the kind of sites that we're going to be looking for. Okay, so this is just a picture of a typical sedimentary basin. This one happens to be right where I live in California. We have a very thick accumulation of sediments. In sedimentary basins, you typically have alternating layers of sandstones and shales corresponding to historical changes in sea level and tectonics and so forth. And so what you would do is you would drill an injection well and then pump CO2 into the sandstone formations. That provides the storage. And then overlying that, you would have a shale or anhydrite or some kind of rock that provides a seal that would prevent the carbon dioxide from escaping and leaking back into the atmosphere. Okay, so that's the idea there. Okay, so now let's look at what happens to CO2 that we're putting underground. Apologies for the dogs. Hopefully they'll stop barking in a minute. And here's where the geologic setting becomes so important. And we're going to divide this into two different phases. We'll first look at the injection phase, what happens, and then we will look at the post-injection phase. Okay, so if we imagine that we have, let's imagine this is our well, and that if we're injecting CO2, we need to displace the water, and CO2 will enter those pore spaces. And it turns out that it doesn't occupy all of the pore spaces. Sort of on average, of the average saturation or the average fraction of the pore space that's filled with CO2 is often around, say, 20 or 30%. If you look at a very small scale at a region that has been invaded by CO2. So you end up with water and CO2 occupying those pores. So this would be if we looked at, say, the scale of, say, centimeters. So the next thing that happens is very important is that, as I mentioned, CO2 is a supercritical fluid. It has a density that's about 2/3 that of water. Meaning it's going to be buoyant. So the CO2 that we're injecting into the well is going to want to float up, and then it will reach the seal, and it will be trapped underneath the seal. So sort of generally you can picture that they'll have some kind of cone-shaped plume around an injection well. But this is a picture where there's no heterogeneity, meaning the rocks are uniform, but in reality we know that rocks are incredibly variable. And we're going to have some portions where we have lower permeability rocks, more silty or shaly, and the CO2 won't get in them. That's shown by the green here. And that these will act as baffles that will sort of trap the CO2, so they basically counteract, at least locally, the effect of gravity. So we have a very complicated shaped plume that is very strongly influenced by the stratigraphy. And then finally, most settings that they're not perfectly flat, like they've been shown there, there's some kind of structure, and that will then guide the CO2 because it will go up under the seal and then want to move up dip. So from a reservoir engineering point of view, these are the kind of processes that we want to understand that will give us information about the sweep efficiency, like how much of the pore space in that underground formation can we access. Okay, so then the second thing is after we've put the CO2 underground, say this takes maybe 30, 40 years or so, we move into the post-injection phase, and things continue to happen even after that. There are a number of trapping mechanisms that are important. And this is a cartoon on the right-hand side, which is not meant to be quantitative, but to illustrate conceptually that there are these post-injection trapping processes that increase storage security. And the kind of processes we're interested in are solubility trapping. So CO2 can dissolve into water, and initially when you contact CO2 and water, you might end up with, say, 2 to 4% of the CO2 actually just almost instantly dissolves. Over time, that fraction can increase. So that's important. And once CO2 is dissolved in the water, it becomes denser and there's no force driving it to leak out of the storage formation. Another very important mechanism is something called residual gas trapping. And this is the process where when you're injecting the CO2, it's connected to each other. It forms like a highway, a connected pathway. But after you stop injecting, the CO2 and water want to rearrange themselves in the pore spaces. And when that happens, you can end up with something called snap-off, which results in all the little bubbles of CO2 being disconnected. And that's called residual gas trapping. And once they're disconnected, they also don't have a good way to flow. And then finally, there can be geochemical reactions that lead to conversion of CO2 into carbonate minerals or other minerals that are, again, are permanently trapped. So again, there's a strong control both from a physical perspective and from a geochemical perspective on the post-injection performance. So what I'm going to do is it's just going to give you an example of a couple of these processes that we've been studying now for quite a long time. But I want to make one more point before we jump into that, is that rock properties at multiple scales impact the performance of the system. So if we think at a pore scale, the detailed shapes of these pores, the sorting of the rocks and so forth, those are going to control how much CO2, what fraction of the pore space could the CO2 occupy, because it takes a lot of work to push the water out of the very tiny pore spaces. So we need to understand at the pore scale. And then here's a wonderful picture of a core. This is one with actually hydrocarbon staining, where you can see that the hydrocarbons are in some layers and other layers, there's no hydrocarbon there. And that's evidence that the laminations in the rock are actually having a very strong influence on where different fluid phases are going to flow. At the centimeter scale, if you look at a well log, you can see all kinds of variations in the rock properties. So this will have an impact at the outcrop scale, and then finally at the full field scale. And I will give you examples from the pore scale and the core scale, and then I'll super quickly wrap up with a little bit of an example from the field scale. Again, all illustrating why it is so important that we have strong geoscience input into the models that are being used to forecast the performance of these projects. Okay, so I'm going to start with the image that actually got me fixated on this topic. This was an image from 2004, and I think it was one of the first images that was taken of using X-ray microtomography of CO2 injection into a rock. And this was done by Liviu Tumutsa, who was one of the pioneers of application of X-ray microtomography to rock studies. And what we can see is on the left side, this was an image of the porosity. So wherever it's dark, it means it's low porosity. Actually, no, I said that wrong. Wherever it's dark, I said it right. Wherever it's dark, it's low porosity. Wherever it's light, it's high porosity. So you can see there was, evidence of laminations in this core. This core was 5 centimeters, or 2 inches about. And we can see that heterogeneity, whoops. And then on the right side, what we can see is that when we injected CO2, so this is the inlet end of the core, this is the outlet, what we can see is that CO2 was not equally going into the core. There are certain portions we couldn't even push it into. And you ended up with this very, structured CO2 in the middle. But you can see right away, because of this rock heterogeneity, we can't actually fill up, even if we think about, okay, we can fill up 20 or 30% of the pore space, there were whole portions of the rock that weren't accessible to the CO2. So I got really fascinated by this. I started out doing largely field work. I would do very large scale field experiments of all kinds of injection processes and so forth. But the frustrating thing about field data is that you have such a limited observation window. You have your injection well where you can get some logs. You might have an observation well, some long distance away where you could measure CO2. You might have some seismic imaging data, but you really don't get a very clear picture. And for me, when I saw this, it's like, oh my goodness, I can see everything. And I can also characterize the rock, so then I could correlate what I can see in terms of the behavior of CO2 to the rock properties. So it was very inspirational to me, and I've kind of been tracking this for a long time. So that was the very first image that I saw. I moved to Stanford in 2007 and built a lab that we could do similar types of core flooding experiments. In my lab, one of the things we wanted to do is to be able to do very, very long-term experiments so that we could achieve steady conditions, which would allow us to make very high precision measurements that take quite a long time. And so that was sort of the key that enabled the kind of experimental work that we've done in our lab. And again, so here are pumps. Yeah, I'm sure lots of you have seen these pumps. And in the background here is a medical scanner. These kind of scanners give you resolution on the order of a fraction of a millimeter. Yeah, so you're not seeing individual pores. You see more the physical structure of the rock, particularly looking at things like laminations and so forth. So anyway, on the right-hand side are these images, and you can see they're clearer and crisper than those old ones. But again, here's a picture showing the porosity. So red is high porosity, and the blue or the yellows are lower porosity. And then if we make a saturation map, so saturation is just the fraction of the pore spaces that are filled with CO2. And again, you see this very nice correlation that where you have high porosity, you also have high saturation. And you can see these very fine features of these rocks. So, okay. So the other kind of tool that we've applied to study these problems are at a much smaller scale. So it turns out you can also do X-ray tomography using synchrotron measurements. And now actually MicroCT is also really opening the door to very high quality measurements at a very small scale. And here what we can actually do is image much smaller samples. So in reality, these two samples you see here on the right are like the size of a pencil eraser. So very small. And there we can do imaging even down to sub-micron resolution that allows us to investigate systems at the pore scale. Okay, so this is an example. So basically we have X-rays from the synchrotron, and then we have a little core holder that then rotates around, and it allows us to do tomographic imaging and imagery construction. Okay, and then finally, another super important tool for these kind of studies are simulation, numerical simulation. This can again be done at a variety of scales. Here's just an illustration of a field scale simulation where the subsurface is characterized at a high spatial resolution. And then that geological model can be used as input to a simulation where we can inject CO2 and see where that would go. And again, we can see in this image that the system here, which was a replica of the Frio Formation, a very important geologic storage formation in the US, that you can see these very complicated plumes, again, highlighting the very important role that a good geologic description can provide. Okay, so those are the tools. Whoops, there we go. Okay, so I've talked about tools and why we're motivated to do this. Now I'm going to jump in and I'm going to give you 3 examples. The first one is going to be to focus on the role of geological heterogeneity on the extent of residual gas trapping. So remember, residual gas trapping was sort of this component here that increases over time and results in the formation of these disconnected blobs or ganglia of CO2. And once they're disconnected, they can't move. So the way this process occurs, though, is illustrated from this image on the left here. This was a very nice publication by Sam Krever. And when you put the CO2 underground, so here's your seal, and so the green is the CO2 plume. This particular example has a dipping structure, so the CO2 wants to migrate up dip. And what happens at the trailing edge of the plume where the CO2 is leaving that volume, that water needs to come in and take its place. So the water is invading the region that used to have more CO2 in it. And as it invades that region, it accelerates this sort of snap-off phenomena that results in the trapping. So what we're going to talk about is how geological heterogeneity influences this process, and is it helpful or harmful? Okay, so again, going back to sort of one of the early images that motivated much more detailed studies. This was an example of a Mount Simon core. So the Mount Simon formation is, again, a very important geological storage formation in the United States. And we can see this image on the top here, right? Okay, so this is, again, looking at the porosity. And you can see lots of, interesting things. Here's some laminations and so forth. But at the end of this core, what you see are some cross-bedding with very intense bands of different saturations. And it turns out this is going to be really important. So what we did is we took this core, we injected CO2 into it, and then we pumped water into it. And basically we displaced as much carbon dioxide as we could. And then at some point you just keep putting more and more water in and nothing changes. So that's your residually trapped CO2. And for this particular rock, the way to think about this graph on the right is that on the x-axis, this is the saturation that in the core during the injection phase. So we've injected CO2 and it's the maximum CO2 saturation that occurred during the injection. And then on the y-axis, we plot the saturation after we've injected the water and we've got residually trapped CO2. So this I starts is initial and then R is residual. So when we first did this experiment, what we found is that we couldn't get any CO2 out of the rock. Okay, so it fell on this. So this is the one-to-one line. So it basically says that the initial and residual CO2 were exactly the same. So it says, wow, once you put CO2 there, it's not going anywhere. It just can't move. But we got curious. We were looking at this and we saw this cross-bedded part, and we said, well, what happens if we just cut that off? So we sawed that off and we repeated the experiment. And then we got a completely different result. Basically, we showed that you only trapped about half of the CO2 that you put into the rock. So much more normal, typical kind of result. Okay, so that said, this heterogeneity is actually really advantageous if we want to have a large amount of residually trapped CO2. So we recently did a study where we took 9 different cores, and we made a very extensive and careful set of measurements. This was done by Cindy Nee, who's now moved on to UT Austin this last year. And so some of these are geologic storage cores. Some were just sort of representative rock types like Berea sandstone that people often use in these laboratory experiments. And we picked them intentionally to have different degrees of heterogeneity. So you can see the rocks there. And yeah, again, what we did is we put the rock into a core holder and flooded it with CO2, and through the use of the X-ray measurements and some analytical approaches we've developed, we could measure basically the porosity, the permeability, and the CO2 saturation of those voxels. So here's an example of some of the data that we got. So I'm showing the data in a slightly different format now. Now what we're going to be looking at is this is the length along the core, okay? So that's so here are the core, the actual cores. So this is the length along the core. This is the CO2 saturation. And this top line here is the average saturation of a slice at the end of the drainage phase, meaning at the end of the time when we've injected CO2. And then on the bottom, we've injected water, and this is the trapped CO2. So again, we did this for lots of different rock types. Just with your eyes right here, you can see that for these 4 rocks, they behaved extremely differently. And we wanted to understand that in greater detail. So this data here, we were looking at this from the perspective of slice average properties of the rock. There's a slice average saturation, for example. But it turns out that we can also look at every individual voxel that we've measured with the X-ray CT, and we can get some more insight into what's happening. Okay, but these again are the same thing. So this is the initial saturation on the x-axis and the residual saturation on the y-axis. And again, for 4 different cores, and you'll notice they have quite different characters. Like this Bentheimer, what we see is there's a very small range of saturation yeah, they're all, very close to the median value. Whereas if we look at rocks like the Fontainebleau or the Chazette, you have a huge range of saturations in these rocks. We were also able, through some analytical techniques we've developed, to assign permeability to these individual voxels. Okay, so each one of these points, these voxels, are also coded by the permeability of that voxel. And what we see is that the portions with very high permeability are at very high saturations, and those with low permeability have low saturations. And what I want you to remember from this graph is just the degree of the spread of this initial saturation distribution. Okay, here it's very little, here it's very a lot, and then here are intermediary. And what we're going to do is we're going to take the standard deviation of the saturation distribution in this core, and we're going to try to correlate that with the amount of trapping that we observed in the core. Okay, so on this x-axis here now is the standard deviation of saturation we measured, and this is the trapping coefficient for the rock that essentially quantifies how much trapping is occurring. And all of these points here, these are the data points. And what we can see is the higher the heterogeneity, or the larger the standard deviation in the saturation, the more trapping we have. Okay, so that's a useful thing. So now we have a method. If you can characterize the heterogeneity of the core, you can figure out how much trapping that you would expect. And again, it's beneficial to have rocks that have higher trapping. So basically what this graph also said is that there are actually 2 components to the trapping. There's the trapping you would expect if you had essentially a homogeneous rock. So all of the trapping that occurs is really due to sort of the pore scale rearrangement of the water and CO2 during this imbibition process, or during the process where water goes into the core. And so for this collection of rocks, it looked like the trapping coefficient for a homogeneous rock would be about 0.46, 0.47. And then beyond that, you can get additional trapping associated with these rocks with more heterogeneity, or rocks where you have a wider distribution of saturation. Okay, so that's one very concrete example of how the details of the geology really have an important impact. So then you can say, well, how important is this residual trapping? Here's some field scale simulations that compare 2 cases. One is where there's no residual trapping, and the other case with a modest amount of residual trapping. And this is looking at what happens to the CO2 plume over a 30-year period after you stop injecting. And what we can see is if this residual trapping mechanism isn't isn't affecting the plume, that this, what was started out as a fairly compact plume, over time it's going to expand and it's going to move up dip and basically spread out over a much larger area, which then requires you to monitor a bigger area and so forth. On the other hand, if we have residual trapping, what we can see is that some rearrangement and movement of the plume occurs, but it's much, much smaller. So basically that CO2 plume is going to stay put where you initially injected it. So these are consequential processes. So now I'm going to talk about something else that's related. So from one perspective, residual trapping is terrific, right? It immobilizes the plume. But if we think about geologic storage, we're imagining, essentially permanent storage on geologic timescales. And the question is this residual trapping really permanent, or is it something that you can create in a laboratory experiment, but it's not going to persist over years or decades or millennia? So we started to think about, well, what kind of mechanisms could remobilize the CO2? And there are a couple of them. One would be Oswald ripening, and I'll describe that in a minute. Another one is potentially the CO2 could interact with the rocks and change the surface characteristics of the rock so that instead of water wanting to be in the tiniest pore spaces, that CO2 would want to be the wetting fluid, and that would result in rearrangement of the CO2 in the pore spaces. And then of course CO2 can continue to dissolve in the brine, and that could have an effect. So other people have studied some of these other processes, but I want to talk about our work on Oswald ripening. So Oswald ripening is a very, very well-known process. And on the right-hand side is an example. So if you imagine if you just had a liquid with a gas in it, and you had a variety of bubbles in here, and small bubbles and bigger bubbles, that over time, what's going to happen is that the big bubble is basically going to accumulate all of the gas from these other two smaller bubbles. And the process that drives this is that the smaller the bubble you have, the greater the capillary pressure. Then capillary pressure is just the difference between the pressure in the liquid phase and the pressure in the gas phase. So you have higher pressure. And so if you look at the amount of CO2 that you can dissolve in the water right next to this bubble, it's going to be slightly higher than the rest of the system because the pressure in this bubble is so much bigger than this one and this one. Okay, so now you have more CO2 dissolved near this bubble, and that's going to create a diffusive gradient, which will allow the CO2 to migrate through the liquid and accumulate in a bigger gas bubble. So in a system where you just have liquid and just have gas, the inevitable consequence is that you end up with just one bubble. And so what we wanted to understand is, how does Oswald ripening work in porous media, geologic materials? And is this an important process? And could it potentially destabilize this residually trapped CO2, which we like because it keeps these smaller, more compact plumes? So that's what I'm going to be talking about. So to do this study, we took a different approach. We used microtomography. In this case, it was at the Advanced Light Source in California. And we were able to obtain very, very high resolution images of 3 different porous media. One was glass beads, one was a Boise sandstone, and one was a Fontainebleau sandstone. And we wanted to study these different systems because each of these has very different pore structure, and so conceivably Oswald ripening could be different in the different ones. Okay, so this is just a little image of the, these are images of individual ganglia of CO2 in the rock. So where you see these colorful things, these are the ganglia of CO2. So we can see in the glass beads that they're that they're quite big, and if it has the same color, it means it's connected. So basically in the glass beads, we saw sort of one big bubble, well, a couple of smaller ones, but big systems. And if you look at the shape of these, they kind of have smoothly curved surfaces and so forth. If we look at the Boise sandstone, and again, this is residually trapped gas, what we see is that we have many smaller ganglia, and many of them occupied only 1 or 2 pores. And then if we go to the Fontainebleau sandstone, that we have more ganglia still, and many of them only occupied single pores. Okay, so that gives us some insight into this process. But if we think about really what's the driving mechanism for Oswald ripening, it's the capillary pressure, and we can calculate the capillary pressure from the curvature of these surfaces. And because these imaging techniques provide such high resolution, we can actually make very beautiful images of these individual ganglia. Okay, so here's the Fontainebleau sandstone, here's the Boise sandstone, and here's the glass beads. So in the glass beads, we can see, you know, they're almost just like bubbles. Nice image up here, okay. But we can see in the Boise that they're much more complicated shape, but still kind of blobby, and, you know, with sort of curved surfaces at the end that, you know, will look a little bit like the ones in the glass beads. But then if we look at the Fontainebleau sandstone, what we see is something different, that it's almost like these pore spaces are triangular shaped pore spaces, and that the curvature, the sort of free interface, whoops, there we go, are these little red interfaces here. So we have very, very high curvature, very high capillary pressure. So the capillary pressure is in and itself not the most important thing. Oswald ripening is driven by differences in capillary pressure. So what this shows over here are examples. These are for the Boise and for the Fontainebleau. So each one of these red lines here corresponds to the capillary pressure of these interfaces for different ganglia. And we can see they really range over a very large value. They're not uniform. So it tells us right away there's a pretty big opportunity for Oswald ripening. And we can see something similar for the Boise sandstone, though it's not quite as broad of a range. So right away from these images, we said that right after the imbibition process occurs, it's possible that you're going to have different capillary pressures, which would be a driving force for Oswald ripening. So we decided to build a pore level model to try to figure out the time scale for these. You know, these are relatively slow processes, and you really can't do dynamic experiments very easily at synchrotron facilities because you only get a short time to do your experiment. So we decided to use a model. And this model told us 2 things. Is one, that you can have multi-bubble equilibrium and porous medium, meaning in bulk liquids, I said it would all just become one bubble. Well, that's not true in porous media. You can maintain individual bubbles. And that's because the shape of the pores is what's determining the capillary pressure. So that's good news for residual trapping, that you can have these individual ganglia won't necessarily accumulate. And then we were able to also look at the time scale over which this happens. So each one of these colors corresponds to different bubbles. So this one, the capillary pressure or the curvature goes down. In others, it goes up, and eventually it converges, and you have this stable multi-bubble equilibrium. And we can see for this very tiny system, this is on the order of 150 microns, that it's sort of on the scale of 10 to the 6 seconds. So you can see right away that these are relatively slow processes. But nevertheless, the expectation is that you achieve this equilibrium and residual gas trapping would be stable. So, but that was for a very, very small and uniform, relatively uniform type of rock. Now let's think about our heterogeneity again, right? So let's picture that we have a rock on like the Fontainebleau, and imagine that is juxtaposed right next to a rock that's like the Boise. So on one side of the system, we would have all these ganglia with very, very high curvature, high capillary pressure. Right next door to it, we would have something with much lower capillary pressure. And so what's going to happen is there's going to be a driving force for CO2 to go from this really fine textured rock with these little triangular pores and drive it over to the Boise, over to the rock like the Boise sandstone. Okay. So we then built a model to study this system. And we can just quickly look at what this looks like. And I'm just about to wrap up, just so I know you don't get anxious. So here's our system. Our initial condition is we have two different rocks with different capillary pressures, one with about 6,000, one with about 4,000 on the other side. We put these two rocks in contact, and eventually the capillary pressure, equilibrium is achieved when the capillary pressure becomes uniform. And so it takes about 10 years in this case, okay? So at the same time, to accommodate this change in capillary pressure, what actually happens is we're gonna have to change the saturation of the rock, okay? So it starts out, the saturations actually weren't so different in this rock, even though the capillary pressure was. And eventually what ends up happening is the CO2 moves from the right-hand side of the system to the left-hand side. So we can have rearrangement of that. Okay, so again, sort of long story short, we could also develop a model for this continuum scale Oswald ripening to calculate the time frames. And what we see here is this is the years towards near equilibrium. Okay, so 10 to the 5 years, so very long time scales. And on this axis, this is the size of the model. Okay, so this is sort of a 1 meter scale system. And what we can see is just even for a 1 meter block, to really achieve this capillary equilibrium, we're talking about very long time scales, 10,000 years, 100,000 years. So what all of this told us is that, you can have, you can have residually trapped CO2, but heterogeneity is going to drive equilibration of the system, but the processes are so slow that one could expect that other things like dissolution and so forth, were more likely to be more important in terms of redistribution of the CO2 than this Oswald ripening process. So yeah, but again, understanding this required understanding the influence of heterogeneity. So I told you I'd say something about field scale simulations. This is just another super simple example, but again, illustrates from a really practical perspective that this is important. We just did simulations of a homogeneous system, a layered system where we had sort of layers of 500 millidarcies, 100 millidarcies, and more extreme contrast of a ratio of 25 to 1 in terms of permeability contrast, and then 100 to 1. Okay, and we can look at the plume migration, and we see for homogeneous systems, the CO2 just wants to rise to the top and spread out under the seal. But in the case where we have a large contrast, the CO2 actually just stays much deeper in the reservoir. And here is showing the amount of dissolved CO2, so we can look at solubility trapping. So what we see is on the right-hand side, this is the plume radius, okay? So after 30 years of injection versus the ratio between the high and low permeability portions. And what we can see is if we have a homogeneous reservoir, in this case, our plume radius was about 550 meters. But if you have this more and more heterogeneity, what one can see is you can really limit the plume footprint. And what we can also see is that there's sort of a sweet spot at like 100-to-1 permeability ratio where you can maximize solubility trapping. Essentially, 20% of the CO2 could be dissolved, shown up here, if you have this sort of favorable heterogeneity. So the bottom line is that, in this case, heterogeneity really helps. So, just wrapping up, I hope that you were interested in these examples of how geological heterogeneity really has a profound impact on plume behavior, and that and the importance of doing this is if we really understand these processes, there will be much greater confidence in the security and permanence of storage. And again, this is ending up just really with a call to arms for those in the geosciences. There's a huge opportunity for you to contribute to this emerging super important technology of carbon capture and storage to help deal with the climate problem. So I'm going to wrap up. I know I took a little too long, but we can do questions.
Thanks very much, Sally. That was really interesting, really fascinating. So we already have some good questions in the Q&A session. I suspect from industry people by the look of it, because they're quite practical. So a couple of questions that are perhaps related are really about, how do we optimize residual trapping? So one question is there an optimal wavelength timescale for heterogeneity in order to promote residual trapping? And I guess a related one is, what's the time frame for Oswald ripening and impact on, say, a 30-year project?
Mm-hmm. Yeah, so maybe starting with the 30-year project. It's really not important on time scale. I mean, it is important that you can get sort of local equilibrium at the millimeter scale, but that doesn't really have a big impact on the operational phase. So Oswald ripening, as far as we know now, is not terribly important or important at all on that time scale. In terms of your question about, is there an optimal kind of heterogeneity that would encourage residual trapping, but at the same time give you good sweep efficiency and all of that? That's a really good question. We haven't gotten that far. I would say we're at the point where we think we understand, we understand the physics, and we've been able to make experiments that, sort of make the case for this. I think the next step is to start looking at what are the optimal structures. And we're actually, I have a collaborative project with the University of Melbourne and Cambridge University with Jerome, where we're going to start looking at some of these issues about, what would be optimal, so as you're searching for a storage site, what are you looking for? Yeah, much the same way we, spend a lot of time that, geologists in the oil and gas industry, we're really crucial to understanding what are those most exciting prospects for oil and gas recovery. That same kind of work needs to be done for CO2 storage.
Thanks. Yeah, there's quite a few questions coming in now. So another question about Oswald ripening: is it sensitive to solution chemistry, such that it could be influenced by the fluid being pumped and be actively regulated? I mean, you've just said it doesn't matter so much, but.
Right. Yeah, probably. I mean, the fluid chemistry is important. If you have a very salty system, you'll have less dissolved CO2. So that will sort of slow down the overall kinetics. So chemistry is important. In terms of sort of some kind of manipulation by, pressure modulos, alternating pressures, I don't think that would have a big effect. Now, changing the pressure will result in rearrangement of the CO2 in the system. The water, is, if you drop the pressure, the bubbles are going to expand and the water has to go somewhere. I think that's a really interesting issue to try to understand. After you've got the CO2 in there, if you drop pressure, could you actually try to increase the storage efficiency?
Thanks, Ellie. We have quite a few questions now. They're really coming in, and we've only got a few minutes left. So I guess I'll try and pick a question that sort of nicely summarizes some of the questions that have come up. So one is a question of how do we incorporate lab scale measurements of heterogeneity into numerical models of field scale heterogeneity as a test of this, to understand the efficiency and permanence of CO2 storage?
Yeah, that's a great question, because obviously we can't represent all of these individual features in numerical simulation models. So basically you need some kind of multi-stage upscaling. So we've recently finished a project again with Cambridge and Imperial looking at that exactly. And you can develop analytical expressions for the effective behavior, things like relative permeability and capillary pressure that include the heterogeneity, and that can then be used as input to larger scale numerical simulations. So yeah, so basically you need to come up with some kind of equivalent continuum behavior over a variety of scales. And as a matter of fact, we're just about to put out our first paper. That's a big collaboration that we did around that. So the kind of consequences that things like relative permeability, which we treat as, as a function of saturation and saturation history. Well, it turns out those are actually dependent on things like flow rate and so forth. So, so it does introduce a significant amount of complexity, and I think it's a real frontier for the scientific community interested in modeling these systems.
There's two questions which are related, which are about the kind of resolution that you're operating at. So one question from Richard Harrison, features operating below your 640 nanometer resolution important in the behavior of the CO2? And a similar question following up, would there be any benefit of a much higher, even a higher resolution analysis to pick up things that you're perhaps not picking up already?
Right. Yeah. There would be. I mean, Charlotte Gehring was the principal author of that paper where we did that work, and you definitely get much better curvature measurements with higher resolution measurements. And for that Fontainebleau sandstone, the 0.64 microns. Oh no. Was that it? Yeah, 0.64 microns. That was just getting to be good enough. So yes, if we have higher resolution measurements, that would be great. Yeah.
And another one which is going up many orders of magnitude larger. So what about the effects of fracture systems at any scale on plume distribution?
Yeah, that's really interesting. So fractured systems are interesting. Even relatively small fractures, there's almost no capillary pressure in those. So all of a sudden, the things that we're so fixated on traditional porous media, capillarity, which really are sort of dominate the behavior, they're not so important in at least the fracture network. It is important in terms of fracture matrix interaction. The other thing is that in porous systems, because capillarity is so strong, it makes gravity less, and gravity is always the same importance, but capillarity can be large relative to the gravity forces. In fracture systems, gravity is going to be really important. So just like a very practical consequence, if you have a horizontal fracture or a dipping fracture, you'll get very different behavior as compared to a vertical fracture. Because in a vertical fracture, all the gas is going to go to the top and the liquid will go to the bottom. So yeah, that's a really messy and interesting problem. Yeah, I've done a little bit of work in that area, but it's really hard to get the quality measurements to do quantitative work.
Okay, well, there's a lovely question. I think maybe it'll be the last one because we've run over a bit here from a fascinating talk, which is really interesting. So is there any way that we could, when we're looking for really good sites for CCS, that we could somehow amend a potential CCS site with a bit of prior injection to improve mineralization So it can feed the site and make it a little bit better at mineralizing when you finally do inject. But a pre-treatment almost.
Yeah, you have to add in an awful lot of materials. So I think that you need to look at cost and benefit to those kind of strategies. And then the other thing is, anytime you inject a sort of complex fluid, particularly with a lot of dissolved species, into a reservoir rock, you really run the risk of plugging it up. And so I think there might be a lot of logistical challenges, but having said that, I think we're at the stage where we get to be as creative and intellectually as adventurous as we can to look at some of these issues. There has been some interesting work on injection of microorganisms, which catalyze the formation of carbonates as a way of trying to block high permeability pathways to mitigate leakage and so forth. The University of Strathclyde have done very nice work in that regard.
There's just a last question. I think this really will have to be the last one. And it's a very practical question. I sense there's a bit of kind of frustration in this question. So at what point will all this theoretical understanding translate into an actual, real, large-scale injection project? I mean, we already have a few, but
yeah, I mean, I think we know plenty to be able to, do, geologic storage projects today. I mean, there are real experts, BGS and, Equinor, I mean, all the companies that have already done. So there's a ton of expertise. I don't think that we should slow down field scale deployments whatsoever, pending, sort of more, thorough understanding of these processes. I don't view these as, big, showstoppers. It's just the more insight that we have, the more of the pore space we can use, the smaller the plume may be, or whatever, or we can accelerate trapping, or, we'll just have more control. Our tools as reservoir engineers will be much better. But we're ready to go. We have been for, 2 decades.
Great. Well, on that really optimistic note, thank you very much for a brilliant talk, which I've personally found really interesting, and I'm sure many others. So let's have a round of applause. Thanks for
yeah. Well, thank you.
I'm sure there are hundreds of people clapping in wherever they are. So thank you very much, Sally.
Okay. Thank you.
Did you want to say something?
Nope, just bye-bye. Thanks to everybody.
Thank you very much, Sally. Great. And just some closing remarks from me. Thanks again to to Sally for speaking, and to everybody who's attended on Zoom and on YouTube. Please check out the webpage, earth2earthseminar.com, and the Twitter feed to keep track of upcoming seminars. We have another set of really great seminars coming up to interest you in these long winter days as we hunker down in this terrible sort of period of lockdown. The next talk will be, I think, on the 28th of January, so not far away. It's by Lindy Elkins-Tanton. So that will be a really interesting talk as well. So I'll wrap it up there, and thank you very much, everybody, for attending, and have a really great afternoon, and hope to see you again in a couple of weeks' time. Thank you.